Okay, welcome back, everyone, to the second talk of today, which is going to be, as foreshadowed in the first talk, will be about reducing the number of qubits in quantum factoring. We're very happy to have André Schrottenloher from University of Rennes and INRIA to give us the talk. So thanks.
Thank you very much. So thank you for the introduction. Thank you also for the invitation. I'm very happy to be here to present this work, to join with Clémence and Pierre-Alain from our team at INRIA in Rennes. So I think we all know in this room that with Schrod's algorithm, we can solve factoring and discrete log problems in polynomial time. So as far as crypto is concerned, we're done. Polynomial time means it's broken and we don't use it anymore for post-quantum crypto, okay. But we might also care about what is the exact cost of this and how soon we can hope to be able to run this on actual quantum computers. In this talk, I will be interested mostly in the space complexity, so the number of qubits we need. Previous estimates and estimates on gate counts that we can compare to are basically, we know that the gate complexity is going to be around n to the squared plus some epsilon if you use very efficient multiplication circuits. And concerning memory, there are different trade-offs. The previous paper by Guidney and Ekera, who did numbers on how to factor RSA moduli of 2048 bits, reached something like 6,000 logical qubits. In this work, we're developing a different approach in which we will compute discrete algorithms in the integers. And we will do that with a number of qubits which scales as the size of the discrete algorithm involved. And this is something we can use afterwards to factor RSA moduli with something like n over 2 plus a negligible factor in qubits. And the gate count is going to be cubic, so it's a little different than the standard Schrod's algorithm, and I will explain some reasons for this. Okay, I thought I would start this talk with some very simple introduction on Schrod's algorithm. That was just an excuse to have some actual quantum part in this talk, because afterwards I have 20 slides of integer arithmetic. Sorry about this. But maybe if this is a bit boring, you can just sleep for this part and then wake up for the arithmetic part afterwards. So let's say we want to find the period of a periodic function which we define on the integers. The function will be defined on integers and has values in modular integers modulo n, and big N here is very large. It's 2048 bits. We want to find the period of this. And Schrod's algorithm is solving this problem with a very, very simple quantum subroutine, which involves Fourier transform, Hadamard transform, then a call to f and a Hadamard Fourier transform again. So this is a very simple algorithm. What it gets you is you do a Fourier sampling of the value of f, and then you measure everything. When you measure, you apply a QFT, you measure the input resistor. What is important in the end is the value you get in the input resistor. And the reason for this is that you will use the periodicity of the function f to create some interference, which will give you a value that is interesting here. To get into slightly more detail, but not too much detail, when you measure the workspace part, which is the value of f of x, you will get up to some normalization factor, a superposition of values, which is something and then the shift, and then double the shift, and so on. And when you do the QFT on such a state, you get interference. So you would expect, you write this down, and you write the amplitude that corresponds to a given integer y for the input part. And if you look at this, you can see that when omega to the ry here, where omega is a root of unity, when it's close to 1, then this is going to be bigger. And when it's not, then this is going to be smaller. So this is basically giving you which values of y you expect to measure. So it doesn't give you exactly the period r when you measure this, but it gives you information on it. And then you can get the period r from this information. So yeah, very simple things. The amplitude gets bigger when you're closer to 1, and this means in this particular case, this value here is closer to an integer. So I didn't say it, but the input resistor M here is it's up to you. The only constraint is that it has, of course, to be bigger than the period. Otherwise, you won't have this nice wrapping up where you start having multiple values that will interfere with each other. But it doesn't need to be much bigger than that. And if you do some measurements, one in Shor's initial algorithm, one or two, multiple ones in some other algorithms, you do some measurements and you can extract information about the period and you can find it with some post-processing. I will not talk about how we do the post-processing in these algorithms because it's going to be classical. As we know, everything's classical is easy. But it's classical and easy, happens to be. In this paper, we are not doing Shor's algorithm on a function defined only on the integers. We're looking at discrete log. But the only difference is that you define this on a two-dimensional space. Because the goal is to find, so if I give you an integer, integers a and j in the group of multiplicative integers modulo n, the goal is to find the discrete log of a respectively to j. And to doing that, you simply define this function of two inputs. And now you can see that it has a hidden period. This hidden period is in dead 2. That's it. That's the only change. So it will slightly modify the structure of the algorithm because now instead of an input register, which is only a single value in Z, you have a pair of values. But it doesn't change much for the implementation of it. And finally, the version of Shor's algorithm that we'll be interested in is the version of Ekera and Hasted. This is a version that optimizes the post-processing part and that optimizes the input register. We need that very much. And the idea is you're going to take an input register, which is really the smallest possible to get information on the period. And the smallest possible is depending on the size of your discrete log. If your discrete log is of size d, like bit size little d, your input register will be of size this for the part x and this for the part y. Intuitively, this is the least you can do to have some wrapping up of the values and to get this nice interference. And you can't do much better than this, and it turns out that doing this is enough to get sufficient interference to get information about the period. You need more than one measurement for this. You need some number which is also going to be small, depending on n. On d, like it's going to be a constant, it's going to be 20 or 50, whatever. And what happens is when you get all these measurements, you do some post-processing of the values, which is based on lattice sieving. And this gives you the period. So this is a version we need. We need something that is really optimized in the input size. And that's it. The other thing we need is to, since we wanted to talk about factoring, is to reduce factoring to a discrete log instance. That might be a bit weird, but this is simply because we're going through this Ekera-Hasted algorithm. And it turns out that when you want to factor the interesting integers, which are, of course, RSA keys, you can reduce this to a discrete log where the discrete log has size n over 2, little n over 2. So imagine your RSA key is of size 2048 bits. The discrete log instance will be a discrete log of size 1024. And the idea is that it simply goes through the fact that the RSA key is a product of two primes of same size. And then if you take an arbitrary g in the group of multiplicative integers, you take the power n. You can realize that this power n is actually a g to the power p plus q mod n, which means the discrete log of g in this group is actually small. It's of size. It's the same size as the at the integers p and q. So it has a small discrete log. And so if you run Ekera-Hasted, you can have an input register of size n over 2 plus t to the low of n. And this is exactly where we get the n over 2 plus t to the low of n of our algorithm. And to give you an idea, for n equal 2048, what is the little low of n? Well, it's going to be whatever you add to 1024 to get this number here. This is an example. You have different possible trade-offs, and you would need 20 runs of the algorithm with such a trade-off. So these are numbers that Martin Ekera computed because you can simulate all of these algorithms and check if it allows you to factor. Okay, so that's was practically the partial source algorithm.
Wait. You're
Yes.
saying you can do all of this with only n/2 qubits? Like a...
I'm not here yet. Yes. I'm only saying the input register is the size n/2 plus c to the 11.
Like the workspace register could be bigger.
Right.
The workspace register is going to be terrible. Yes.
Yes. Good.
Yes. So that was really just limiting the input size. That's
Got it.
So far so good.
Good.
Let's go to implementing actually the function f. As you noticed in this algorithm, everything is simple except the f part. QFT and Hadamard transform are supposed to be efficiently implementable, but we will have to focus on this, and this is actually a classical arithmetic circuit. So let's focus on the f part. Usually what we do is we reduce exponentiation modulo n to a controlled multi-product where we simply pre-compute powers of the numbers that we are supposed to exponentiate. And then, depending on the bits of our input register, we control products by constants in some accumulator. So the accumulator, which I say it starts at 1, of course, in this accumulator we'll control a product by the value g, and then g squared, and then g4, and so on. Now, what happens is actually, usually in Schwartz algorithm, we don't really care about the input register, because if you use all the control qubits only once here, you can do what's called a semi-classical Fourier transform, which will transform this into an input register with only a single qubit that you reuse and that you reset all the time. So actually, we don't really care that much about the input, usually, because it's a single qubit. And what happens is here. It's how we can compute f, and especially these modular multiplications. And usually, this takes us 2n bits. We need n bits for the value of f, and we need n bits for ancilla qubits. Now I'm going to move on to the version of Schwartz algorithm that will allow us to reduce this space complexity. And that's a version where you compress the output of the function f. So the idea will be that if you replace the function f by anything composed with f, it's still a periodic function. And it happens that if the thing you compose with f is a good hash function of some sorts, Schwartz algorithm still works exactly in the same way. Ikera-Hastad, and pretty much anything that contains this periodic period finding subroutine, they still work in the same way. And you can formalize this. It's a paper by me and Schlipper. You can formalize this if you define a universal hash function family. You pick a small constant, and your constant can even be 1. And the hash function family is compressing your outputs into orbit strings. And the idea is that if you replace each call of the period finding subroutine by picking a hash function at random and then performing the subroutine with it and then measuring, you get actually a distribution of measurement outputs, which is the same as before. And so it immediately, like generically, allows you to run any Shor-like algorithm with this. It's not exactly the same distribution as before, though. The only modification is that you obtain a higher probability to measure 0. But if you remove all the zeros, and the highest possible is when error equals 1, you get one half of 0 results. If you remove all the zeros, then you get the same. Sorry.
Why do you have a high probability
of measuring 0?
collisions? More collisions?
No, it's not collisions. It's that basically.
It's because the zero component of the Fourier transform is large because you have a lot of elements that you still have in your superposition.
I see.
Yeah, so you just have to add a constant to get up to the right average, and that corresponds to the zero component of the Fourier transform.
Okay, so question was why so much probability of measuring 0, and then Greg answered the question, which was
it's just
random interference.
Yeah, the zero component is the average, and since you have a lot of things in your thing now, because you're compressing down to a small output, so you have a lot of elements of the superposition, the average is larger.
Yeah, I think another way to see this is that in the zero component you get basically if you compress to a single bit, and in the zero component you basically get the weight of your function. You can also see that if you compress to a single bit, but the function is very unbalanced, it's not going to work anymore. There is this kind of problem as well, and when it doesn't work anymore, it's just because the zero component is eating up all the amplitude. But when it's correctly balanced, and if it's a good hash function, it's supposed to work in the same way. And it's very nice that you get the same distribution because then you can just use the previous work in kind of black box way. So that's what we want to use. Of course, there is a little problem here that we don't have really a guarantee at this point that we're able to compute the compressed function without just computing the function first and then compressing it, which wouldn't really help in the space complexity. But that will be the idea. And more precisely, in our work, we compress by truncating to the least significant bits, which means we take the result of the exponentiation and we take it modulo 2 to the r. And r is a constant, which is 22 for us for technical reasons, but it's a constant. And the idea is that if the initial function is nice enough, this will still allow us to use the compression theorem or an adaptation of it. And so we are still guaranteed that if we do that, we can obtain measurement results that we can just feed through the post-processing routine, and it will work in the same way. Just have to remove the zeros, of course. So that's the conclusion of this part, is that if we combine correctly Hastad and the compression, we get factoring in n/2 plus e to the power n space and discrete log, which are even better because it depends on the size of discrete log. What remains, of course, is to implement this. Are we sure that we can compute the exponentiation, mod n, and then reduced and then compressed using a small total space? And this is where we enter the part on integer arithmetic. So if you have any questions, that's a good moment. But otherwise, 20 slides of integers.
Wait, okay, just to be clear. So in your theorem, like the factor result just follows from the discrete log result, right?
Exactly.
Okay.
The factoring is a byproduct of the discrete log result. Actually, it's a bit better to just look at the discrete log and then you say, well, factoring is n/2 here. Yep. Okay, let's go. So how do we compress a workspace? Using some arithmetic tools. First of all, I would like to convince you that this is not surprising. Because you can combine known results of circuit complexity to actually get something which is polynomial time and little ancilla space to compute this compressed function. The idea is that we know that there exists a log n depth arithmetic circuit that will compute the exponentiation, and so also the exponentiation and all its bits. And if you have such a circuit, then you can just do a depth first exploration of it. And this will immediately give you an algorithm with polynomial time in n and log n space that will compute the bits of the exponentiation. And you can make such an algorithm reversible, and you can keep the time in poly n, and you can keep the memory negligible in n. So you actually get something that is polynomial and that has already small ancilla space. It's not like surprising from a complexity, circuit complexity point of view. Of course, the problem that remains is to have a polynomial that is actually not too large, and also to have a little O of n that is actually small when we plug in n equal 2048. Okay, but this is not entirely surprising. Actually, the circuits that do this in logarithmic depths, they use the same tools that we use in the end, which is going to be the residue number system. So this is where we really enter the arithmetic part. So using residue number systems is actually, this is everywhere in circuit complexity. This is used to optimize arithmetic operations, to perform them in low depth, and to obtain some results of circuit complexity with low depth. The idea is that you can represent an integer using its residues modulo a set of small primes. So you fix a set of small primes. You know that Chinese remainder theorem gives you a bijection between integers modulo the product of the primes and then tuples of integers modulo the small primes. And this bijection is constructive, which means you can just go into this direction by taking the modulo to the pi, and then you can go into the other direction, reconstructing this from the residues with this formula. I'm going to start introducing notations for all these large cofactors, but the idea is that everything that is not in red is pre-computed at this point, pre-computed constants in the whole algorithm. This pretty much depends on our input. This is an integer, big integer that we reconstruct from the residues, and this pretty much depends on our input. The RNS is such that if your integer has dn bits, for some reason, I'm taking dn bits, and d is smaller than n, so it's like n squared bits at most. The number of primes you have is dn over log factor, and these primes have log n bits. So they are really small, like logarithmically small in the input bit size. And this is usually used to reduce the depth of circuits. Because when you compute on the residues, you're able to compute in low depth. And then you can reconstruct your integer from the residues. And in our case, we absolutely don't do that. We use this instead to compute in low width. So that would be the main result that helps in this algorithm, is that if you're able to, if you have this big integer, which arrives from somewhere, and if you're able to compute the residues reversibly with a small additional space, then you're able to compute y mod n mod 2 to the r with also a circuit with log n space, like small space. If you use that, you can directly plug it in the factoring circuit, and you will have a low additional space.
What does non-exact mean?
I'm going to get here. Non-exact as in it doesn't work on all inputs. So to apply this result, you simply recall that we want to compute this multi-product of integers. And now I have removed the modulo n here, which means y is actually just a big integer. It's a big integer where, well, all these integers have n bits, but you have like n or d or n of them. So it's an integer of n squared bits at most. And computing its residues, well, it's also like a controlled multi-product, except that you're reducing everything modulo a small prime p. So this is what we want to compute. This is y, and we want to compute y mod n mod something. And these are the residues that we're able to compute. You can see that since we're computing mod p here, everything is in log n space. So this is space efficient. And computing them is pretty much equivalent to what we did in standard Shor's algorithm. You can, for example, do a control multi-product with many multiplications. You can do a bit better than that with optimizations, but I won't go into these details. So computing a residue basically takes you log n space and a time which is depending on the number of integers you're multiplying here. So something like d, because this is your input bit size. So this is what we do in the actual algorithm. And if we run the total cost estimate of this, it's going to be basically the cost of computing all the residues. I will explain why. And this gives you then d times, n d times d up to log factors. And this is where we get the n cube of factoring. Yes?
Just to check, so for you, you only need the product of the p's to be bigger than big N, right? Is that true?
I need the product of the p's to be bigger than this large number here. But this large number here at this point is an integer.
Good.
And it's bigger than big N.
Yeah, got it.
This is why I have removed the mod n here. I will compute this. I'm basically like this. We will compute this large integer, even though we will never store it, really. We compute only on the residues. But this is what we use to connect between the values modulo n and then the values modulo p in this algorithm. So yeah, that's really important.
Okay.
And this is where we get the n cube of factoring. And fun fact, this is an n cube that we can't really reduce. Like in Shor's algorithm for factoring, when you do it with multiplications mod n, you get n cube if you do it with schoolbook multiplications, and you get better if you do it with improved multiplication circuits. But in our case, the asymptotics is n cube. And it doesn't really get better than this because we're really limited by the way we use the RNS. Okay, and now even more arithmetic, because I need to explain how we do this, actually. There will be 5 slides to explain a very complicated method, and then another slide to explain how Craig Kidney does better than us, of course. So let's do our method first. So we want to reduce the computation of this number where y is very big, but it's never really here in the memory. And then reduce by n, and then some bits of this. The first step is to go back to the CRT formula, where we have these cofactors, and then y can be written as a sum of all the residues multiplied by cofactors, pre-computed constants. And then it was mod big M, where M is a product of all the primes, if you remember. And we write this in an explicit way. This is also a well-known classical technique. If you do that, then you will have some quotient here that you need to compute. And it happens that this quotient is both a small value, so it's fine, it fits in memory. And also it can be computed explicitly from the residues. And that is also nice, because then we're also reducing this to computation of the residues. So when we compute all the residues, we can basically compute the quotient and then compute the rest of the algorithm at the same time. So we can write this very explicitly. Of course, at this point, the formula is explicit, but we are still not able to write y in memory entirely because y is extremely big. It's it's n squared bits, so it's extremely big. Eventually, what we want to compute is y mod n and then some bits of it. So we can rewrite this. And we can write this in a very naive way, just by saying, well, this is y, and then there is a quotient of y by n, and then there is a times n. And if we reduce this modulo 2 to the r, so taking a few bits of the result, we get something like y mod 2 to the r. This is actually easy to compute. It's just we reduce everything modulo 2 to the r, so that's going to be fine. And that takes constant space, so that's fine. There is a value here like n mod 2 to the r, which is also a constant. Lots of constants everywhere. And then there is this quotient. So we reduce the problem to basically computing this quotient, y divided by n, and then modulo 2 to the r. So some bits of y divided by n. And so now we're here, and we still need to do more arithmetic. No questions? OK. So we're here, quotient. The next trick is to replace this division by n, which is not really nice, by a division by a power of 2. Dividing by a power of 2 is nice, because this just means shifting the bits. So you can really do that easily when you have an integer in memory. And that's what's called Barrett reduction, also something very well known in circuit design. So you take a very large t, and it's very large because the integers involved are very large. The y here is very large, and you can have an equality. So if it's large enough, you can have an equality between this, the quotient, the actual quotient by n, and then this, which is, well, multiplying by, again, a very big pre-computed constant, and then shifting the bits. And then we get even more ugly formulas, because we will replace the y here by its RNS representation. So it gets ugly, but what you have to see here is that essentially the RNS representation is replacing y by a big sum of things. And in these things, you have the residues, and then you have big cofactors. This is also a big cofactor. So at this point here, what we get is a sum of integers which depends on the RNS residues, and all these integers are very big and big constants. All of this QM is also computed by us, so we also get something which is big and a big constant. And then we take this sum, and then we want to take some bits in this sum, because this is what the division by 2 to the t and then the floor means in the end. We just want to take some bits in a sum of very large integers, and these bits are located somewhere in this sum. Okay? So well, we can do that. But this is where things will become slightly less exact than before, and slightly heuristic as well. It happens that when you have a sum of large integers, and you take many of them, in our case, like n squared, and these integers are very large, and you want to compute some bits, but they are located somewhere, you can actually not care about all the least significant bits in this sum. And that's just because carries, when you do a sum, they don't propagate that much. In more detail, you can just take this and truncate everything to some position. You truncate most of the least significant bits, and the only window size that you need to keep when you're summing actually nd integers in our case, so n squared basically. The only window size you need to keep is log n. It's of the order of log n bits. So we have reduced everything to computing the residues because they're still here, and then controlling, like using these residues to control the addition of integers in a sum. But at this point, the sum is simply a sum of numbers which are quite small. They are size big O of log n, so they are small. They will fit in memory. And there is nothing more to be done here. When we compute this sum, we will get a value that is some bits of the quotient of y divided by n, and then we go back, and this gives us y mod n mod 2 to the r. So this is the last arithmetic trick, yes?
Wait, so I just wanted to make sure I was following there. So t is like n squared. So even like any one of those terms in the sum is like you need n squared bits to write it.
Yes.
You can't even write down one of them.
No, you can't write anything. All the terms in the sum, they are all very big integers.
Yeah.
I mean, even before t, they were very big integers because they were basically of the order of these terms are the order of m, which is the RNS product, and it's also a size n squared bits. All of this gets very, very big. But in the end, these integers are very big, but the part you're interested in is very small. And this is enough for you, because sums are nice, because carriers don't propagate. Too much, at least. But this is heuristic, of course. I mean, this is heuristic and also non-exact. You can't guarantee that this is always work. And it's fine, because you don't need it to always work. When you run Shor's algorithm, you just need to work with large constant probability. Because you're simply using this on the superposition of all inputs. If you have a circuit that fails on some of these inputs, you will simply deviate from the expected quantum state, but just by some amount. And this is fine. You can still run you can still do measurement results and still run the post-processing with this non-exact setting. So that was the technical the technical core of our approach. In the same paper, we tried to do some like concrete estimates, concrete in the sense of logical circuits. Didn't do anything related to physical implementations, and we just wanted to have an understanding of the numbers and see if they were really bigger than previous estimates for Shor's algorithm. They are a bit bigger. So for a single exponentiation circuit, we computed something like 2 to the 35 Toffoli gate, which means 32 billion something. And we also needed more runs, because since we're using a carrier Hastad, we need 40 runs. And by the way, this is negligible in n. That's the problem with constant factors, right? Okay, yeah, so we were still happy that we went already below 2048 bits. So the RSA key size is 2048 bits, but the number of qubits you need to run the factoring circuit is smaller than that. And we were really happy with this. That was 1 year ago. Since then, of course, Craig Gidney did much better work. So he improved both the arithmetic circuits and also came up with all the designs for physical estimates of this. So I will just talk briefly about the arithmetic parts, because they are very nice ideas as well. So basically, the reduction in arithmetic brings you to a circuit with 1400 qubits, and much better count in Toffoli gates, and also a better count in the number of runs you need to make before you expect to succeed in the Hecker-Hastad algorithm. All of this, combined with the physical estimates, brought Craig to this very impressive number of million noisy physical qubits. And so, as I said, I would just talk briefly about the improvements in the arithmetic and how my 10 previous slides could have been actually simpler. So there are very nice ideas. One of them is to, instead of compute the least significant bits of the exponentiation output, to compute the most significant bits. Because if you do that, and if you recall this formula that is very important for us, the explicit Chinese remainder theorem, if it happens that if you choose the residue number system appropriately, you can make it so that this factor will not intervene when you take the modulo n. So if basically when you take the modulo n of this, if m mod n is very small compared to n, then you can obtain the same value. You can directly compute the MSBs on this. And that is much better. I mean, there are simply steps that you don't need to do. In particular, you don't need to compute this quotient. You're saving some space, and that's really nice. And also the second step that is also really nice is that when you get to this sum, you basically get a sum of integers which are controlled by the RNS residues. And you can approximate this sum in a simpler way that we did with Barrett reduction by just shifting things. And then you compute a sum of these integers modulo n and directly shift back to have the result. Basically, this gives you a very much more direct process of accumulation in which you have this register and you just, depending on the bits of the residues, just summing things into this. Yeah.
But in the end, don't you care, because you're a hash function, don't you actually care about like y mod n mod 2 to the 22? So you actually care about the least significant bits of this, or?
Well, we care about the least significant bits, but Craig uses the most significant bits.
Also, you change the hash function.
And yes, that's another change, and that's where you can make the arithmetic a bit better than ours, which I find really nice. Because you indeed have the choice, right? And you could take pretty much any hash function that suits your needs in that case. I mean, you don't even have to truncate to some of the bits. You could do something, I don't know, weirder. But it just happens that this is nice. It works fine. So sorry, yes, Craig.
Do we have like, I mean, it seems to just work, so I'm not like worried about it. But I was just wondering if there's any like evidence that like this is sufficiently, this doesn't have any smaller periods or something like that. Like, there's nothing weird that goes on because it's not a random hash function, right? We're just like taking some bits.
Yes.
And I am virtually certain that this is fine. I think it's like very clear that it's fine, but I'm just curious if we have some like theoretical evidence that this is fine.
So I don't have very strong. I think having very strong theoretical evidence would require to solve very difficult problems in arithmetic. But they're like, if you're happy with heuristics like the ones used in polar throw factoring, where you say, well, the function that exponentiates is practically random, right? If you look at the numbers that it obtains, then this is sufficient. Because if your function behaves like in a random way, then truncating the bits is also like a random thing. And this was basically the heuristic we tried to base on at the end. But otherwise, you can also, you can just run experiments and see that it seems to be fine.
I think, hasn't it been shown that like the bits of modular exponentiation are hardcore, and that maybe says that? Okay. No.
That may be related to, I mean, hardcore things means we relate this also to a computational problem. I'm also fine with that.
Okay, yeah.
So yeah, maybe.
Okay, yeah, I was just curious.
Yes, so that would close the arithmetic part. So I encourage you to look at this paper from Craig, which is very nice. And I'm going to the conclusion of this talk. I have some more like very, very brief things to say on this topic. So first of all, a summary that this was actually, as you have seen, a talk on circuit design and circuit arithmetic disguised as a quantum computing talk. What happened is that if you use a function with small output space, quantum period finding doesn't really care. And this was enough. And also, if you use an arithmetic circuit that is approximate, that doesn't work for all the inputs, only like with some good probability, period finding also doesn't care. So you can use some circuit designs which would be really, really bad as classical circuit designs, but they are fine in the setting of quantum computing. And I find this really fun. What also happens is that we actually were repurposing known techniques which are used for low-depth classical circuits into low-width quantum circuits. And that may be also something that will happen in other settings. I wanted to talk briefly about elliptic curves because there are questions about can we do that with elliptic curves? And the short answer is no. Just because if you look at an elliptic curve group, you don't have residue number systems. Of course, they are not integers anymore. And we are very much dependent on arithmetic on integers. for our approach. But I can also say that there was a work with a circuit of log squared n depth. And if you do the same reasoning as that I explained before, when you just reduce this to a low width circuit, then you can say, I'm confident to say that indeed there is a circuit which will give you n plus little of n space, and then a number of gates which is super polynomial, which might not really be practical, especially if you run the numbers, and I'm really not sure about this little here. Because n is really supposed to be small. In elliptic curves, in factoring n is 2048, in elliptic curves it's supposed to be 256. So we're also getting to a point where the constants really matter a lot.
Wait, how are these compatible? Like n space, log squared n depth. Like how can the number of gates be n to the log n? Eating the circuit over and over?
No, are you talking about, sorry, the question is how these numbers are compatible. Are you talking about the log square and depth circuit, which is different from this one?
Oh.
Yes. That would be using the simple translation of a very low depth circuit into a very low width algorithm.
Oh.
Where you simply,
Got it.
Same as I did, same as I told before with, but before we had log n depth, and so we got polynomial number of gates. So we could be a bit more confident. And here, I'm not even confident that we can have this in polynomial number of gates. I'm really not sure of this. We've tried working on this a bit, but I'm really at the moment, I'm really almost sure that if you want to get this asymptotic complexity, even asymptotic, not even practical necessarily, but this asymptotic complexity in space, you will most certainly lose the polynomial gate complexity, and most certainly not obtain something that is cubic in n, which would care about yes.
Is the log squared n depth coming from having to do a GCD? Or are there other reasons?
Frankly, so the question is where does the log square n depth come from? Frankly, I'm not really sure. I think when you I think it's simply when you do factoring, you reduce to the control multiproduct. And control multiproduct, you can reduce this to, you can use the RNS to reduce this to very low depth. When you do elliptic curve discrete log, you have a control multi-addition of points. You don't have the RNS, so you will have a tree. Basically, you reduce this to a tree of addition of points. And I'm guessing you can do the addition of points in a log n depth, but then you get also a log n overhead for the tree. And we're stuck here.
Right.
But we're also kind of stuck here when we care about stuck on this kind of thing when we care about the small space complexity. So we don't know. Maybe what will happen is that we can still compress, reduce the space, but we reduce it to something linear in n, but which is not n. And that would be already nice, I guess, if you get 2n bits for the elliptic curves. And we might obtain a polynomial gate count with that. But I'm not even sure about what the polynomial would look like. So that's pretty much open at this moment. Otherwise, last thing I have to say is that as a cryptographer, this paper is not on archive. I promise that it should be one day, but at the moment it's on ePrint, so you will find it here. And if you have any questions, I'd be happy to answer. Thank you.
So thanks for a great talk. We have some time for questions. So maybe I'll try to pass the mic around to people who have questions.
So if my goal is just to come up with the first break of a classical, go beyond classical basically for either breaking RSA or elliptic curve crypto, which one, based on our current understanding of quantum algorithms, which one's going to be first?
So good question. Based on my current understanding, neither of them. You should start with discrete logs in the integers. And that's for reasons I didn't talk enough about. Where are we? Oh, this is. So when you get to the discrete log in the integers, you have instances of discrete log where the ambient group size is very large, the discrete log size, the discrete log is basically living in a small subgroup, and the size is smaller. And this gives you actually very good numbers. In number of qubits, for example, we have like, I don't know, something like 700 qubits for something that is classically secure. And I'm sure that Craig would have better than this. So yeah, so this gives you instances of hard problems which are easier than factoring for the quantum parts and have the same hardness as far as classical is concerned. The thing is, people are less interested in this because, of course, discrete logs in the integers are not very used anymore in crypto. People use discrete logs on elliptic curves. So the cryptographic interest of this is smaller, much smaller. But as a computational problem, I think it's much better.
How does this compare to this Jacobi factoring stuff?
I absolutely don't know. So we have 1 week to figure it out with Greg. I don't know. I think it competes with the Jacobi factoring because the scaling. So when you do discrete log in ZN, the scaling you can have would be that you want the discrete log instance in your small subgroup to be as hard as the discrete log basically running the number field sieve on a large ambient group. The number field sieve has a sub-exponential complexity, so you can get the small subgroup of sub-exponential size, like a 2 to z something, like the 2 to the d here. D would be sub-exponential in n, and can get to this. So you could get to a space complexity, technically sub-exponential also in the parameter, and I think this is close to what you get with a Jacobi factoring circuit. That might actually be for like the same very fundamental reasons. I'm not sure about this, but I think it's like competing.
Thanks.
Can I just say one quick thing about that for 2 seconds?
Do you disagree?
I just want to say super quickly about Jacobi. I think my current understanding is that I think the gate count would probably be lower for Jacobi, but the thing that's a little tricky is it's not entirely clear actually how big we need to go for hardness for Jacobi. So it's certainly possible that we would need more qubits for Jacobi if it turns out like the size we need to go to is bigger than what we need to go to for these like small discrete logs. So.
Yes.
Yeah.
Yeah, you also have a very good gate count. That's.
But I could certainly imagine that the qubit count would be better for this. I just don't know, but it's possible.
I have to ask Craig.
Sorry, I just wanted to clarify what you just said about discrete log, and also the second part of the question had to do with can you whether you can say that these are in some sense the best possible bounds? Is that completely clear that you can't go below these kinds of? But coming back to the discrete log, so you said, well, you could have discrete log in a much smaller subgroup, but then you're presumably saying there's a trade-off in the sense that the quantum algorithm works faster if there's a smaller subgroup, but somehow there's a trade-off saying that the classical algorithm doesn't only depend on the size of the subgroup. So what's that trade-off that you're thinking of?
So as far as I know, which is not much, what you get is basically you have an ambient group with a large n of size, a large prime of size 20, 48 bits, like a safe prime group, and then the subgroup will be the multiplicative subgroup modulo a prime factor, like a prime number which would be of size. Basically, the subgroup would be of size 20, 24 bits. So you get a classical. You get the best of both because the classical complexity of solving a discrete log in a subgroup is going to be basically the cost of polar throw algorithm, and it's going to be d over 2 in that case, so like 112 bits. And at the same time, the complexity of using the number field sieve to solve the discrete log will be also of the same order. That's what people use when they use discrete logs in the integers like this. And they just do this because you don't want, I mean, you want to make things faster. So working in a smaller subgroup makes it faster because then you have smaller exponentiations to compute when you do this. And what was the other part of the question again?
Is it sort of a theorem that you can't go below,
I don't know. So if you go below d/2, then you start doing better. I mean, you would have a better classical algorithm than polar throw in the subgroup, and I think this would be quite surprising. So I don't think you go below d/2. And then if if this is the limit, I'm not sure. I'm not sure. I think like from a design perspective, not from a theoretical perspective, but from a circuit design perspective, I think it doesn't get better than this. But from a complexity theory perspective, I don't know.
Thanks.
Wait, just to clarify the last thing you said, it's like you're saying if you had a quantum algorithm with better than d/2, then you would get a better classical algorithm for discrete log, or?
Well, I mean that if you get a better space complexity than d/2,
yeah,
then you can just simulate this algorithm with a classical space with a 2 to the d/2 times polynomial factor, and then you're starting to go beyond what you're supposed to be able to do classically.
Got it.
Which would be nice. But, I will dot this.
More questions? Thanks.
For the elliptic curve case, do you know if there's like any performance difference depending on whether the elliptic curves the points have integer coefficients versus polynomial coefficients?
There have been works on both, and I don't remember how the performances compare. What I do remember is that with elliptic curves, the complexity is basically n cubed, but n is very small, and then the gate counts that you get are not so large. They are quite nice. They are quite competitive with factoring. I think even better in some instances. And I think that's true both for the elliptic curves with on integers or like on polynomials. Yeah, but as far as we're concerned, this doesn't help us in any way at the moment. But
any more questions? Okay, if not, let's thank André again, and we'll go to lunch. So we'll resume today at 2 p.m. And just as a reminder, we're still soliciting